There is a question circulating through security research communities, privacy advocacy groups, and technology forums that deserves a serious, grounded answer. When you disable Microsoft Recall, when you find the setting, toggle it off, and trust that the feature has stopped, does it actually stop? The concern is not hypothetical. It is not the product of internet paranoia or reflexive distrust of large technology companies. It emerged from direct technical examination of how Windows components behave, from the documented behavior of background services, and from the genuine difficulty of establishing, with precision, exactly what continues to run on a system after a user believes they have turned something off. Microsoft Recall was one of the most controversial features Microsoft has announced in years. The promise was extraordinary. An AI-powered photographic memory for your computer, capable of finding anything you have ever seen on your screen through a simple natural language search. The concern was immediate and intense. A system that takes periodic screenshots of everything on your display, processes them, and stores them in a searchable database represents a fundamentally new kind of data collection. One that sits at the boundary between genuinely useful productivity technology and a surveillance architecture operating on your own machine. Users who decided they did not want Recall turned to the settings panel and disabled it. Many of them believed that was the end of the story. Whether it was, and what the answer reveals about how modern AI-powered operating systems actually work, is what this discussion is going to examine with precision and without assumption. Microsoft Recall was announced in May 2024 as a flagship feature of the Copilot Plus PC initiative, a new category of Windows devices defined by the presence of a neural processing unit capable of at least 40 trillion operations per second. This hardware requirement was not incidental. Recall's core functionality depends on on-device AI processing that would be impractically slow without dedicated neural processing hardware. The concept behind Recall is elegant in its ambition. At regular intervals, the default being every few seconds during active use, Recall captures a snapshot of what is displayed on the screen. These snapshots are not stored as simple image files. They are processed by on-device AI models that extract semantic information from the visual content, the text visible on screen, the applications running, the websites being browsed, the documents being edited, the people appearing in images or video calls. This extracted information is indexed into a searchable database that associates the content of what was on screen with a timestamp and contextual metadata. The result in Microsoft's vision is a computing experience where nothing is ever truly lost. A user who read an article 3 weeks ago but cannot remember where they found it can search for it using a description of its content. A user who saw a product in a browser window but closed the tab can retrieve it by describing what they remember seeing. A user who received information in a meeting recorded on screen can find that information by searching for terms they remember from the conversation. The productivity promise is real and addresses a frustration that is genuinely common among knowledge workers who process large volumes of information across many applications and sessions. The architectural decisions Microsoft made in designing Recall are significant and deserve precise description. The snapshot capture and processing occur locally on the device. The neural processing unit performs the AI inference required to extract semantic content from each snapshot without sending image data to Microsoft's cloud servers. The resulting database, with the indexed content derived from those snapshots, is stored locally on the device's storage drive, encrypted, and protected by Windows Hello authentication requirements that prevent other user accounts or unauthorized processes from accessing it. These architectural choices distinguish Recall from a cloud-based surveillance system, which it is not. Microsoft's design intention was explicitly to create a capability that processes sensitive visual data locally, keeping that data on the user's device rather than transmitting it to remote infrastructure. This distinction is important and frequently lost in discussions that conflate Recall with cloud-based data collection. Recall is also distinct from Windows Search, which indexes file names, document contents, and email metadata to enable conventional file search. Windows Search has operated on Windows for many years, and its behavior is well documented and well understood. Recall operates at a different level, capturing the visual state of the screen rather than the content of stored files, and its indexing produces a different kind of database that represents a history of screen states rather than a catalog of stored documents. Understanding these distinctions is the prerequisite for examining what happens when Recall is disabled, because the question of what stops and what continues requires understanding which components are involved in producing Recall's functionality. The question of what disabling Recall actually does is where the technical complexity and the legitimate controversy begins. Microsoft provides users with several mechanisms for controlling Recall. The primary control surface is within the Windows 11 settings interface, where a toggle allows users to pause or disable Recall's snapshot capture. When this toggle is set to the disabled position, Microsoft's documented behavior is that Recall stops capturing new snapshots. The AI processing that extracts semantic content from screen states stops executing. New content is not added to the recall database. This is what users who disable recall reasonably expect to happen, and on the surface, it is what Microsoft's documentation describes. The complexity arises when the question is extended beyond snapshot capture to the underlying system components that support recall's functionality. Recall is not a single self-contained application. It is a feature implemented across multiple Windows system components, services, scheduled tasks, storage subsystems, and AI model infrastructure that collectively produce the recall user experience. When a user disables recall through the settings toggle, the question of precisely which of these components stops executing and which continues to run in a reduced or standby capacity is one that requires technical examination rather than assumption. Security researchers who examined Windows builds containing recall functionality identified that certain system services associated with recall's operation continued to be present and registered in the Windows service infrastructure, even when recall was toggled off. The presence of a registered service does not necessarily mean that service is actively executing. Windows maintains registrations for many services that run only when triggered by specific conditions. But the presence of these service registrations created legitimate questions about whether the boundary between disabled and uninstalled was as clean as users might expect. The distinction between disabling a feature and uninstalling its supporting components is a genuine and important one in software engineering. When a user disables a Windows feature through a settings toggle, they are typically instructing the operating system to stop producing the user-visible output of that feature. The infrastructure that supports the feature, the service registrations, the scheduled task entries, the storage allocation, the AI model files, may remain on the system in a dormant state, available to be reactivated if the user re-enables the feature or if system conditions trigger a service restart. This architecture exists for a practical reason. Removing and reinstalling complex system components every time a user toggles a feature on and off would be slow, resource-intensive, and potentially destabilizing. It is more efficient to maintain the infrastructure in place and simply stop the feature's primary execution loop when the user disables it. This is a common and legitimate software engineering approach. The concern it generates is not that the approach is inherently malicious, but that it creates a gap between user expectation, I turned this off so it has stopped, and system reality. The infrastructure that runs this feature is still present and registered, even if its primary function is paused. The indexing question adds another layer. Recall's searchable database is built and maintained through an indexing process. When recall is disabled, new indexing of screen content stops. But the existing database, the historical record of screen states captured before the user disabled recall, remains on the device. Depending on whether the user has specifically chosen to delete this stored data, a significant historical record of their screen activity may persist on the device in the recall database even after the feature is disabled. Microsoft's interface provides options for managing and deleting this stored data, but accessing and using those options requires deliberate user action beyond simply toggling the feature off. The recall controversy did not emerge from a single finding or a single moment. It built through a sequence of events that created and amplified legitimate concern while also generating a degree of misunderstanding and overclaimed alarm that complicated the conversation. The initial announcement of recall in May 2024 was met with immediate and intense skepticism from the security research community. The fundamental concern was architectural. A system designed to take periodic screenshots of everything on a user's screen and store that content in a searchable database creates a single high-value target for malicious software. An attacker who gains access to the recall database or who installs software capable of querying it does not need to monitor the victim's future activity. They have access to a comprehensive historical record of everything that has appeared on that computer's screen. Within days of the announcement, security researchers had demonstrated that in early preview builds, the recall database was stored in a location and format accessible to other applications running under the same user account. This meant that malware operating with standard user privileges, not requiring administrative elevation, could potentially read the recall database and exfiltrate its contents. The demonstration was technically reproducible and represented a genuine security concern that the initial recall implementation had not adequately addressed. The response from the security community was swift and broadly covered in technology media. The concern was not that Microsoft had built recall with malicious intent. The concern was that the implementation created a security surface of extraordinary sensitivity, a database containing a searchable history of everything on the screen, including passwords entered in web forms that password managers autofilled, banking information displayed in browser sessions, confidential documents opened in productivity applications, and private communications visible in messaging applications, without adequate access controls to prevent malicious software from exploiting it. Microsoft responded by delaying Recall's planned launch, moving it from a default on feature to an opt-in feature and committing to implement additional security measures. The security improvements that followed included encrypting the recall database and requiring Windows Hello biometric authentication to decrypt and access it. These changes addressed the most acute security concern, preventing standard malware from directly reading the database, though researchers noted that an attacker who had already compromised the user's Windows Hello credentials, or who could execute code in the context of an authenticated user session, retained potential access pathways. The controversy around whether disabling recall truly stops its operation emerged from a different line of research. One focused not on the security of an active recall installation, but on the behavior of Windows systems where recall had been toggled off. Researchers examining Windows component behavior documented that certain services and tasks associated with recall functionality retained registrations in the Windows service and task scheduling infrastructure after recall was disabled through the settings interface. Reports characterizing this as proof that recall continues scanning files after being disabled circulated widely and generated significant alarm. This is the point where the distinction between verified technical findings and interpretive overclaim becomes critically important. The presence of service registrations for recall-related components after the feature is disabled is a verified observation. The characterization of this as evidence that recall is actively scanning files while disabled is an interpretation that goes beyond what the evidence directly demonstrates. A registered service that is not in an active running state is not executing. The question of whether any recall-associated component transitions from a registered but inactive state to an actively executing state under conditions other than user re-enablement is one that requires careful and specific technical investigation to answer with confidence. The public debate that followed did not always maintain this distinction. Reports that recall was scanning files despite being disabled generated significant media coverage, and the nuance between service registration and active execution was frequently lost in that coverage. This does not mean the underlying concern was unfounded. The architecture of recall's component persistence after disabling does represent a legitimate question about the precision of user control, but it does mean that the most alarming characterizations of the situation went further than the available evidence strictly supported. Microsoft's handling of the recall controversy provides a case study in how a large technology company responds when a significant product announcement generates sustained and technically substantive criticism. The initial response to the security research demonstrating the recall database's accessibility was the delay of recall's launch. This decision, made within weeks of the May 2024 announcement, was significant because it acknowledged that the criticism had identified a real problem rather than dismissing the concerns as misunderstanding or media sensationalism. Microsoft's public statement cited the need to deliver a higher quality, more secure experience, which was interpreted by the security research community as recognition that the initial implementation required substantial revision. The security improvements Microsoft committed to and subsequently implemented addressed several of the most specific concerns researchers had raised. The recall database encryption, protected by the device's trusted platform module and requiring Windows Hello authentication for access, represents a genuine improvement over the initial implementation's access controls. The change to opt-in rather than default on enrollment significantly altered the population of users who would have recall active without having made a conscious choice to enable it. Microsoft's privacy documentation for recall is more detailed than the company's documentation for many Windows features. The documentation specifies what types of content recall explicitly excludes from its snapshot capture. Private browsing sessions in supported browsers are excluded, certain categories of sensitive content are filtered, and DRM-protected video content is excluded. These exclusions are documented and represent deliberate design decisions to limit the most sensitive categories of screen content from entering the recall database. On the specific question of what continues to run when recall is disabled, Microsoft's position is that the feature's snapshot capture stops when the user disables it. The company's documentation does not provide granular detail about the behavior of every system component associated with recall when the feature is in a disabled state, which is itself a source of user frustration. The gap between high-level assurances and specific technical documentation of component behavior is where much of the controversy lives. Microsoft has also provided users with tools to manage and delete the data recall has collected. The settings interface for recall includes options to delete all stored snapshots, delete snapshots from specific time periods, and filter out specific applications or websites from future capture. These controls exist and function, but they require users to navigate into the recall settings specifically. They are not presented prominently in the feature's disable flow in a way that would ensure users who turn recall off also consider whether to delete the data it has collected. The broader context of Microsoft's response is the Secure Future Initiative, the company-wide security commitment announced in late 2023. Recall's privacy and security challenges arrived at a moment when Microsoft had already publicly committed to treating security as its highest engineering priority. The gap between that commitment and the initial Recall implementation created reputational pressure that almost certainly contributed to the seriousness and speed of Microsoft's response to the criticism. The Recall controversy, examined at its deepest level, is not primarily about Microsoft or about one feature in one operating system. It is about a fundamental tension that is becoming increasingly central to computing as artificial intelligence is woven into the platforms people use every day. AI features that are genuinely useful require data, not in the abstract sense that data is a vague input to distant systems, but in the immediate sense that AI operating on your computer, doing useful things on your behalf, needs to observe what you are doing in order to assist you with it. An AI that can find anything you have seen on your screen requires a system that captures what you have seen on your screen. An AI that can anticipate what you need next requires a system that understands what you have been doing. An AI that can summarize your recent work requires a system that has access to your recent work. The data requirement of useful AI and the privacy expectations of computer users are in tension that cannot be fully resolved by architecture alone. Local processing, keeping data on the device rather than transmitting it to cloud servers, addresses one dimension of that tension by reducing the population of entities who have access to the data. But it does not eliminate the fundamental question: does the user understand what is being collected, where it is stored, how it can be accessed, and what happens to it when the feature is turned off? The Recall experience suggests that the answer, for many users, is no. The feature was announced with enthusiasm for its capabilities, and with architectural descriptions that emphasized its local processing design. What was less prominently communicated was the specificity of what the Recall database contains, the conditions under which it can be accessed by other processes, and the precise behavior of its components across different operational states. The gap between what users understood and what the system was doing produced a controversy that a more transparent communication approach might have reduced, even if the underlying technical architecture had remained identical. The trajectory of AI integration in operating systems points toward more of these situations, not fewer. As AI capabilities deepen and as the value they provide depends increasingly on rich behavioral data, the questions users will need to answer become more consequential. What is this AI observing? Where is that observation stored? Who can access it? What happens when I try to stop it? Is the stopping actually complete? These are not questions that can be answered by reading a privacy policy document that the vast majority of users will never read. They require transparency mechanisms built into the product itself, clear, specific, user-accessible explanations of what each AI feature observes, stores, and does, presented at the moment those features are encountered rather than buried in documentation that exists but is practically invisible. The regulatory environment is evolving toward requiring exactly this kind of transparency. Data protection authorities in multiple jurisdictions have begun examining AI features in consumer operating systems. The requirements they develop will shape how features like Recall are disclosed, controlled, and documented in ways that the current voluntary disclosure model does not enforce. Microsoft Recall is not the end of this story. It is the beginning of a longer and more consequential conversation about what it means to have an intelligent operating system, one that learns, observes, and remembers, and what users are entitled to know and control about that intelligence. The controversy that Recall generated was, in a sense, productive. It produced security improvements that made the feature meaningfully safer than its initial implementation. It produced a shift from default on to opt-in enrollment that gave users a more deliberate choice. It produced a public debate about the appropriate boundaries of AI observation in consumer computing that the industry needed to have. And it produced a level of scrutiny directed at how Windows privacy settings actually function that revealed gaps between user expectation and system behavior that deserved to be closed. What it did not produce, and what the broader industry has not yet produced, is a clear, universally applicable standard for what transparency looks like when an AI feature is deeply integrated into an operating system. What does it mean to truly disable something in a world where its infrastructure remains registered and available? What does it mean to have control over your data when that data exists in a database that persists after you have turned off the feature that created it? What does it mean to trust a privacy setting when the technical reality of what that setting does requires engineering expertise to fully understand? These are not rhetorical questions. They are engineering and policy challenges that the companies building AI-powered operating systems must answer. Not in documentation that users will not read, but in interfaces that communicate clearly and completely at the moment users are making decisions. The stakes of getting this right are significant. The AI capabilities being built into operating systems represent a genuine expansion of what computers can do for the people who use them. That expansion is worth having. But it is only worth having if users can trust that their understanding of what their computer is doing matches what their computer is actually doing. Because an intelligent operating system that users cannot fully understand, cannot fully control, and cannot fully trust is not a more capable tool. It is simply a more sophisticated unknown, sitting on the desk, watching the screen, and waiting to be understood.